Okay, today we're going to learn about the standard deviation of the residuals. We're going to learn how to calculate it and interpret it. And so what is the standard deviation of the residuals? Well, it gives the approximate size of the residuals. It's like an average size of the residuals. And when it is large, it means the model is not working as well. Or it's not working well. Okay, you also have to consider the size of whatever it is you're predicting. So if it's something that has larger measurements, you would not be as concerned with a larger S. So make sure to consider the size of your Y variable. And we talked about that yesterday in class as well. So how do you calculate it? Well, first of all, we're actually going to use computer output for the most part. But as always, I'm going to show you the formula so you understand what it is that you're using and what you're talking about, etc. So computer output. Eventually, we will use something called the Lin-Reg t-test. So we'll save that for later unless you want to explore that on your own. But it's something I teach later in the year. So the Lin-Reg t-test, which we'll use later. But it does compute it for you as well. So this is the formula. S is equal to, and it's the square root of the summation of your residuals squared, divided by n minus 2. So those are the degrees of freedom for this, n minus 2. So another way to think about this, it would be the square root of the sum of all your individual y's minus their predicted y's for that x squared. So we computed that in class yesterday, so you know what that looks like, divided by n minus 2. So it's basically just the average size of your residuals. Okay, so calculate and interpret the standard deviation of the residuals for the Honda CR-V data. So I'm going to pause right now and we're going to do a little activity in our calculators building on what we did yesterday. And the sum of, we'll sum it up and we'll figure it out, and we'll come back in just a second. Okay, so we have entered our CR-V data, which we actually did yesterday. So I want to show you sort of what this looks like. So we have our x's in list 1, our explanatory variable, of course, our response variable in list 2, and then what I have in list 3 is where I actually ran the regression for every x value. So I input x into the actual function y sub 1 that we had stored. Then I did the actual y minus the predicted y. So I did list 2 minus list 3. Then I squared the residuals. Then I will sum the residuals squared. So let's go to that feature. So I'm going to go to my list feature because that's where I can square the list. So do second stat, go over to math. It's going to be sum, which is option 5, and I'm going to do list 5, and I want to sum it. So that's the summation of all the residuals squared. I will divide that by n minus 2. Since there were 11 observations, that'll be 9, and then I need to square root that, and I get 971.65. So that is the standard deviation, and we've actually worked it all out from start to finish. Now, usually you will be given that on a regression output, okay? So let's go back to here and fill in the rest of this. So calculate and interpret the standard deviation of the residuals for the Honda CR-V data. So we determined that that value was S is equal to 971.65. Okay, so if we know the miles driven, we could use a linear regression model which has more predictive power than simply using y-hat to make predictions or y-bar to make predictions. So essentially the average error, or that's just your residuals, is $971.65, because remember we were trying to predict the advertised selling price for certain miles. So on average it was off almost $1,000, which is not terrible, but I would say it's somewhat large for this particular application. Okay, let's go to the next page. And we're going to fill in some blanks here. Okay, suppose that you see a used Honda CR-V for sale. Just you're driving about, you see it there, and you want to predict the asking price for the CR-V. So our best estimate would be y-bar. In other words, if we didn't have any predictive model, the best guess you could possibly make would be y-bar. And guys, there's a reason I'm talking about y-bar, because in a minute we're going to learn something called R-square, and R-square essentially tells you how much better your predictive model using a linear relationship is working versus just using the average y, which would be the average advertised price. So we would expect our error using this model to be rather large, because the model using y-bar does not have much predictive power. It probably is better, though, than no model at all. So how much better would our predictions be if we knew how many miles that had been driven? So if we know the number of miles, we could use the linear regression model. And guys, this is really just our least squares regression line, which has more predictive power than simply using y-bar to make predictions. So that probably makes sense. And we're going to do an activity where we actually explore what R-squared is, but let me tell you, basically filling in the blanks here. So what is the coefficient of determination R-squared? So students always get R, which is the correlation coefficient, confused with R-squared, which is the coefficient of determination. So let's make sure you understand that. So how do you calculate and interpret R-squared? And then, like I said, we're going to do an activity. So R-squared is the fraction of the variation in the values of y that is accounted for by the least squares regression line. Of y on x. Remember, that's just how we say that. So we interpret R-squared as the percent of variation in y explained by the least squares regression line. Or you could just say, or the model relating x and y. So all those are appropriate. Okay, now let's talk about R and R-squared, how they're related, and various characteristics of those. Okay, R-squared really is simply R raised to the second power. That seems so simplistic, but they do mean different things, so we'll talk about that. R is not the same as slope, so I want to reiterate this from yesterday. R is not the same as slope, but they do have the same sign. And it's because of the direction. So if you have a positive association, that means the direction is upward as you go from left to right. That means your R should also be positive. If you know R-squared, to find R, take the square root of R-squared. That seems simple. But then you have to make sure to use the sign from slope, because you won't know whether the relationship is for a positive association or a negative association that R-squared is referring to. Because R-squared will always be positive, obviously. So R squared and S both measure how well the least squares regression line models the data. So I talked about that earlier. And S is in the units of the response variable because it's the typical size of the error for predicting Y. But R squared and R are standardized and have no units. So neither R squared, S, or R address the form. The residual plot is imperative for doing that. And then what you're looking for there is if the scatter plot or the residual plot, it is a scatter plot, so I'll give you that. It's a scatter plot of X versus your residuals. And we did that yesterday, is not random. Or has a distinct pattern. The linear model is not a good fit. Then the linear model is not a good fit. And this is all because I told you yesterday that when you run the regression, a linear regression, it should almost cancel out that linear pattern. And if it doesn't, then that means that the linear model is not a good fit, is some other type of relationship, some sort of curve, or maybe it's just that the model doesn't work well for all the X values for the model. So you are going to do homework number 5, and that is it for today. Thanks so much.